SwayamPrabha. Digital India. Educated India.
Hello and welcome to lecture 32. We are discussing about the selection of design parameters. In last lecture we have solved a numerical, that's what is based on calculation of our critical velocity and radial equilibrium. Let's start with say one more numerical. Just look at this. Say here this is what is a figure, that's what is giving us information saying the stator and rotor gap of axial flow compressor stage where total temperature is 550 Kelvin, rotational speed is 25,000 rpm. Following data, that's what are available at the mid radius now. Say absolute velocity at the entry it is 300 meter per second. My absolute flow angle at the mid station is 30 degree. Static density at the mid station is 5.8 kg per meter cube. And up to tip tangential or whirl velocity component variation, that's what is given by formula say Cw into square root of R equal to constant. The rotor blade inlet or say metal angle is constant from hub to tip and rotor mean radius incidence angle is 0. If the average specific heat ratio is 1.4, calculate following variables: hub and tip rotor blade incidence angles, rotor inlet total pressure difference, that's what is P0 at the tip minus P0 at the hub, at hub and tip radius. Assume average density magnitude to be that at the mid radius. So this numerical, that's what is somewhat different from what all we have discussed in the last class. Let's see what all information that's what is available with us. It says my total temperature is 550 Kelvin, rotational speed is given, that's what is say 25,000 rpm. My entry absolute velocity is 300 meter per second. My absolute flow angle is 30 degree. Density at the mid station it is given, and my whirl variation, that's what is not say your free vortex kind of configuration. Here it is given Cw into square root of R equal to constant. The information that's what is given at mid section, my incidence angle is 0 and we need to calculate what will be the incidence angle at the hub and the tip. We also need to calculate what will be your total pressure difference. So you can say this is what is a different kind of numerical where we are looking for other properties. Okay, so let's try to understand how do we solve this kind of numericals. So what all we are looking for is we are looking for incidence angle calculation at hub and tip. What we know, in order to calculate that say incidence angle, we must know what will be our inlet blade angle and outlet blade angle. In order to calculate those, we need to have our velocity components and we must know what is our velocity triangle. Okay. Now here in this case, if you look at, we can say my peripheral speed, that's what can be calculated based on available radius, and my rotational speed is known to me. Okay. The whirl component, that's what it says, it is following Cw into square root of r equal to constant. So that's what will be helping us for calculation of our whirl component. Okay, so this is what all will be helping us in sense of calculating velocity components. But very important velocity component, that's what is missing, that is axial velocity. Now the question is, how do we calculate our axial velocity? Angles are unknown, few velocity components are known, but at the same time what we know, we have our radial equilibrium equation. That's what will be helping us for calculation of our axial velocity. It may be varying from hub to tip, or it may be remains constant. We need to check with. But just understand, because this is what is Cw into square root of r equal to constant, that definitely says my axial velocity will not remains constant. So that's what is a hint. We need to calculate what will be my metal blade angle, and based on that we will try to calculate what is our incidence angle. So this is what is our strategy for say solution 1. Same way we are looking for calculation of delta P0. We can understand, if we are looking for say delta P0, that is total pressure at the hub, if we are looking for total pressure at the tip, we must know what will be our static pressure. Again, we are having the correlation, that's what is correlating our total pressure and static pressure. That's what we say our critical Mach number. Now in order to calculate that critical Mach number, we must know what are our velocities and temperature. So let's see how do we proceed with. It says like we are looking for rotor inlet total pressure ratio, okay, or pressure difference. That's what is looking for say my critical velocity and static pressure. So we must know what will be our static pressure at mid station, or maybe hub station, or at the tip station. Here the hint is given, at mid station density is known to us and temperature also is given to us. So we can say that's what will be helping us for calculating our static pressure at one location. We can use our fundamentals of radial equilibrium equation, and based on that we will try to calculate all velocity components, and from that we will be calculating our critical velocity ratio, and from that we can calculate what is our total pressure difference. So let's begin with say for first solution. So what all information, that's what is given to us, we can plot this kind of velocity triangle. So what it says, my alpha angle, that's what is known to us. So alpha 1, that's what is given 30 degree. Okay. Now at mid station my diameter is known, my speed, that's what is known, so you can calculate what will be my u. So let's try to understand how do we proceed with. So here in this case, from velocity triangle we can write down our whirl component at the mid station, that's what will be given by C1 into sine alpha m. Okay, because at mid station I know what is my absolute velocity, I know what is my say absolute flow angle. So this data it's known to me. Say it says C1 equal to 300 meter per second and my absolute flow angle is say 30 degree. And at mid radius I know what is my radius, that's what is 0.12 meter. So if I will be putting this, it says we can calculate what will be my Cw. So if we are calculating that part, it says my Cw into square root of m, that's what is constant. So basically we will try to calculate first what is our constant. So it says 300 into sine 30 into this is what is square root of 0.12. It says my constant as 51.96. Okay. Now what is known to me, my Cw into r equal to constant. So we can say my Cw, that's what is given by 51.96 divided by square root of r. Now it says if I am looking for what will be my whirl component at hub, I can calculate by putting hub radius, I can calculate at tip by putting tip radius. So let's see, suppose if you are considering this as our case, at hub we know our radius as 0.06 meter. At mid station our radius is 0.12 and at the tip station my radius is 0.18. So if we are putting that into formulation, it says my whirl component at the hub is 212.13 meter per second. My CW at the mid station, that's what is 150 meter per second, and my CW at the tip, that's what is 122.47 meter per second. So you're having higher whirl component or whirl component, that's what is present at the hub, and lower whirl component, that's what is present at the tip. Okay, so this is what is a calculation for our whirl component. Now, in order to do calculation for our flow angle, we are looking for our axial velocity. Now, what we know from our formulation of radial equilibrium equation or say vortex energy equation, we can write down this is what is a known formula for us. So, in place of my CW, we can write down that's what is given by some constant divided by square root of R. So, if we are putting in this equation and if we will try to put in the formulation form, it says half d axial velocity square divided by dr, that's what is given by minus 1 by 2 c square by r square. Now, here in this case we can do the integration again, since at mid station my axial velocity, that's what we can calculate. So, let me put this as a mid station to some radius r. Here also we are putting at mid station to some radius r. So, that is what is giving me my axial velocity at any radial location as say c square at mid station minus c square by rm plus c square by r. Now, here in this case it says we are not having any information about axial velocity at the mid station. But if you look at from our fundamental understanding, the angle alpha, that's what is known to me, that is say 30 degree. Now, we have already calculated our CW1 at the mid station. So, based on my formula, I can write down my axial velocity at the mid station, that's what is given by C1 cos alpha m. So, this C1, that's what is known to me, it is 300 meter per second, my alpha is 30 degree. It says my axial velocity at the mid station is coming to be 259.80 meter per second. Okay. Now, once this is what is known to us, we can write down in the form of this formula. It says my CA square or my axial velocity at any radius, that's what is given in the form of some radius. So, this is what is the formula. Okay. So, you can understand the basic application of radial equilibrium with your vortex energy equation, that's what is always necessary. We need to have some background of mathematical formulation in sense of integration and differentiation. That's what will be helping us in order to get the solution in a proper way. So, this is what is my axial velocity at particular radial location. Now, we can say my radius for hub, my radius for mean and radius at the tip station, they are known to me. It says at hub it is 0.06 meter, at mid it is 0.12 meter and at the tip it is 0.18 meter. So, we can say this is what we can write down and we can calculate our axial velocity at the hub, that's what is coming 300 meter per second. At the tip station this is coming 244.95 meter per second. Okay. So, do not consider or do not assume axial velocity to be constant. Be careful. You are given the variation of whirl component and that too it is in a formulation form. That's what is giving you hint my axial velocity is not remaining constant. Okay. Now, if this is what is your case, we can calculate what is our peripheral speed. Okay. So, in order to calculate that, we know what is our rotational speed, that's what is 25,000. my hub radius is known. That's what will give me my peripheral speed at the hub station, at mid station and at the tip station. So we can say at hub it is 157.08 meter per second, at mid station it is 314.16 meter per second, and at the tip station that's what is say 471.24 meter per second. Okay. Now you can say we are able to calculate different velocity components. This is what will be helping us in sense of calculating different flow angles. So let's try to look at this part. What it says, at mid radius my incidence angle, that's what is given to be 0. So we can say my beta 1 at mid station, that's what is equal to beta 1 dash at mid station. Now if we are putting our velocity triangle at the mid station, so what we know is my mean peripheral speed, it is 314.16 meter per second, my CW is 140 meter per second, and my axial velocity is a 259.81. So if we are putting all together, that's what will be giving me this kind of velocity triangle. Okay, so it's always advisable you make your velocity triangle freehand. That's what will help you in sense of calculating different flow angles. So for this velocity triangle, my beta 1, that's what is given by u mean tan inverse u mean minus CW mean divided by CA mean. Now these numbers are known to us, so we can calculate our beta 1 mean, that's what is 32.28 degree. Okay, here in this case my incidence angle, that's what is given 0, so we can write down my beta 1 dash, that's what is coming as 32.28 degree. Okay, now let's try to look at what is happening at the hub. So we have done our calculation for wall component, it is 212.13 meter per second. My peripheral speed at the hub is 157.08 meter per second, and my axial velocity we have calculated, it is 300 meter per second. Be careful here. Here if you look at carefully, my whirl component, that's what is larger compared to my peripheral speed. So your velocity triangle, that will be changing accordingly. Do not make any mistake here. So here if you look at, based on this number, roughly we can say this is what will be my velocity triangle. Make a freehand, that's what will be helping you in sense of understanding. Same way I can put my equation for beta 1 at the hub, it is tan inverse UH minus CW divided by your CAH. Now here in this case my CW, that's what is say it is coming to be higher, that's what will be giving me my beta 1 at the hub as minus 10.39 degree. Okay, what we are asked to calculate for, that says I need to calculate what is my incidence angle at the hub. So if we are putting, that's what is given by beta 1 minus beta 1 dash. So this beta 1 at hub we have calculated, it is minus 10 degree, and this is what is say it is given, it is a constant, so that's what is 32.28. so it says my incidence angle, that's what is coming minus 42.28. remember, this is what is numerical, this kind of numbers may not come in actual condition. Okay, but for understanding you can say this is how we are calculating our incidence angle at the hub. Okay, in line to that we can do our calculation for my tip station. At tip station we know what is our whirl component, we know what is our peripheral speed. It says my whirl velocity is 122.47 meter per second, my peripheral speed is 471.24 meter per second, and my axial velocity at the tip is 244.95 meter per second. So based on this data, if I am putting my velocity triangle, then this is what will be my velocity triangle. Okay. So here in this case we are not having the situation as we have seen for our hub. You can see here my peripheral speed, that's what is larger, and my whirl component, that's what is smaller. So you can see here, so this portion, that's what is representing my whirl component. Okay, and this is what is my peripheral speed. So if that's what is your case, you can write down by 10 beta 1, that's what is u tip minus Cw divided by Ca. These numbers, they are known to us, so we can do our calculation for. That's what it says. We are getting our incidence angle to be 22.61. Okay, so this is what will be giving us idea about what we say in sense of our variation of incidence angle at hub, variation of our incidence angle at the tip. Okay. Now the second part for this numerical, as we have discussed, that's where we are looking for variation of delta P0, okay, at hub, and what will be the variation of my delta P0, or we can say what is my P0 at the hub and what is my P0 at the tip. Okay, so here in this case, as we have discussed, let's start with the solution for. So very first thing what we are looking for is for calculation of our critical velocity component. Now in order to calculate our critical velocity component, we must have the temperature value. Okay, so at mid station I can write down my static temperature, that's what is given by total temperature minus C1 square by 2 Cp. If we are putting that, it says my static temperature, that's what is coming as 505.2 Kelvin. Okay. Now from our fundamental understanding, we can do our calculation for say my static pressure at the mid station as say density into R into T static. So we can say that's what is coming as say 840.99 kilopascal. So now at mid station, my static pressure, that's what is known to me. Okay, so here in this numerical, my temperature, static temperature, that's what is not given straight away, but remember that's what is related in sense of say my total temperature and absolute velocity. Okay, so what all data, that's what is given to you, just try to locate that, put it on diagram or write down what all data, that's what is given to us, and based on that you move ahead with. Okay. Now in order to do our calculation for the variation of my static pressure at the tip or mean or say maybe hub, we can use our radial equilibrium equation. It says my dP by dr, that's what is given by say rho Cw square by r. Now what is given to us? We know what is our whirl component, that's what is say constant divided by square root of r. That's what we can write down in this formula, and if we are integrating that from say mean station, because at mean station my static pressure is known to me. Be careful at what location you are known with the pressure or temperature, accordingly you need to decide with your limit. Same way for axial velocity. So here in this case at mid station my static pressure is known to me, so I can calculate my static pressure variation at any station by integrating this form. It says my static pressure at any location, that's what is given by say Pm plus rho c square by say Rm minus rho c square by R. Now the mean radius, that's what is known to us. So if we will be putting all this together, that's what is giving me my static pressure variation with the radius. So here if you look at, this is what is a formula for the variation of my static pressure at particular radius. Okay. Now let's put, we are looking for our variation of, or say we are looking for our static pressure at the hub. So if we are putting my radius as 0.06, we are getting our static pressure at the hub. If we are putting our radius at the tip as 0.18, we are getting our static pressure at the tip. Okay. So now my static pressure at the hub and tip, they are known to us. Okay. Now in order to calculate your critical velocity, we must know what all are the velocity components. So here in this case, if you are looking for say absolute velocity at the hub, we can write down that's nothing but Cw square by Ca square, and that's what will give me my absolute velocity component as say 367.72 meter per second. Same way my absolute velocity at the tip, it is 273.86 meter per second. My critical velocity at the tip, we can calculate, it is square root gamma 2 gamma r at T static divided by gamma plus 1. This temperature, static temperature at the tip, that's what is known to us. So we can write down this equation and we'll get 429.13 meter per second. So now if we are looking for say calculation of our critical Mach number at the hub, we can write down that by say C1 by VCR. Same way for tip, we can write down C1 by VCR. So since my absolute velocities are known to me, so I can calculate what will be my critical Mach number at the hub and what will be my critical Mach number at the tip, and that's what is coming say 0.856 and 0.638. Now once this critical Mach number, that's what is known to us, we know there is a relation between say my total pressure and my static pressure in the formula for critical Mach number. So if you are putting these numbers, it says this is what is P divided by this. Here at hub my critical Mach number is 0.856. If you are putting that, this is what it says is coming in sense of my megapascal pressure. Okay. Here at tip also we can do our calculation. So if we are putting all this together, that's what is saying like my delta P0, that's what is coming to be say 10.192 kilopascal. Okay. So let's do the compilation of what all we have learned. Say we have calculated our say tangential velocity variation, that's what is Cw into square root of r equal to constant. That constant we have calculated, it is 51.96. We have calculated our axial velocity variation at mid station, hub station and tip station. Then we have calculated our incidence angle at the hub. We have calculated our incidence angle at the tip. We have calculated static pressure and at hub as well as our static pressure at the tip, and finally we have calculated our delta P0. Okay. So this is how what all we need to use in sense of our understanding for what all formulas we have learned up till now. So this is what is end of this particular session. Thank you very much for your attention.